Welcome to this video where we look at the analog to digital converters. In my previous video, I discussed the digital to analog converters, and we extend our discussion to the analog to digital converters. Basically, analog to digital converters are devices that will be able to take up an analog input voltage and produce a digital output code, which represents the analog input. And therefore, the device is able to take up an analog input voltage and convert it into a digital output code that is a representation of the analog signal. We look at a number of analog to digital converters, and the first such a converter is what we call the digital ramp converter. The digital ramp converter is as shown in my screen or on my screen. And as you can see, from the converter, it has a comparator that is able to compare two analog signals, VA and VB, and give an output EOC. It has an AND gate, a 3-input AND gate, and the output of the AND gate is a clock signal to a counter, so that this is our counter, and the output of the AND gate is the clock signal to the counter. The output of the counter is fed into a digital to analog converter. That means the digital equivalent stored in the counter is converted into analog form to obtain our analog signal, VB. Then the inputs to the AND gate are one, the output of the comparator, a clock input signal, and the output of a NOT gate. The comparator works as follows. If VA is greater than VB, if VA is greater than VB, then end of conversion will be high. Remember, the comparator takes VA and compares with VB, where VA is the analog input signal to be converted into digital form. If VA is greater than VB, end of conversion or the output of the comparator is high. If VA is less than or equal to VB, then end of conversion is going to be low or a 0. Then the output of the AND gate is going to be high so long as all its 3 inputs are high. And then the reset pin is used to reset the counter to start from 0. This is the operation of the digital ramp ADC. Initially, the clock pulse or a start pulse is sent to the reset pin of the counter and also an input to the NOT gate. When that reset pulse was a 1, a high, gets to the counter, it clears the counter to start from 0. At the same time, that 1 is an input to the NOT gate, and the output of the NOT gate will be 0. That means the output of the AND gate will be 0, since one of its input is a 0, and therefore that output of the AND gate being 0 will not be able to clock the counter, and the counter will store a 0. That 0 is converted into analog form through the DAC, such that now our VB is 0. VA is greater than 0 since VA is the analog signal to be converted into digital form. And that point, then our EOC is 1. When the start pulse is cleared, is a 0, then the input of the NOT gate will be a 0, and its output will now be a 1. When a clock input comes as a 1, all the inputs to the AND gate will be 1, and therefore the output will also be a 1. That 1 is able to clock the counter, and then our counter counts 1. That 1 is converted into its analog equivalent, a voltage VB, and VB is compared with VA. If VA is still greater than VB, then in the next clock cycle, the output of the AND gate will be a 1, makes the counter to count 2, 2 converted into analog voltage, that analog voltage compared to VA to produce an output EOC. This will continue as long as the output of the comparator is a 1. When VB is greater than or equal to VA, then end of conversion now becomes 0. And when the end of conversion is 0, the output of the AND gate will be now a 0, since one of its input is a 0. That 0 will no longer clock the counter, and whatever the counter stores or had stored will be the digital equivalent of the analog signal VA. And through that, we are able to obtain a digital code which is equivalent to the analog input voltage VA. And that is the operation of the digital ramp converter in its operation on converting an analog voltage to a digital code. The second type of the ADC is what we call the successive approximation converter. The successive approximation converter. And this is the construction of the successive approximation converter. It has a comparator similar to that of the previous converter. It has a control logic circuit, a register or a memory unit, and a digital to analog converter. The output of the comparator is an input to the control logic circuit, and the other inputs to the control logic circuit are a clock input signal and a start pulse. The outputs of the control logic signal is an end of conversion signal and digital code that is sent to the memory unit or the register. The digital code stored in the register is sent to the DAC for conversion into analog form. And this is the operation of the successive approximation converter ADC. The analog signal to be converted into digital form is fed into the positive input terminal of the comparator as the signal VA. So the signal VA, holds the analog input signal. Initially, the control logic circuit sets the most significant bit of the register high and all the other bits low. For example, if the register is a 4-bit register, it sets the most significant bit 1 and all the other bits as 0 to obtain 1, 0, 0. This is sent into the DAC, which converts it into analog form to obtain our voltage VB. VA and VB are compared, and if VB is greater than VA, that means our choice of 1, 0, 0, 0 is smaller in terms of comparison with the analog input voltage VA. And what happens is that the output of the comparator goes low and causes the control logic to clear the most significant back to low. Otherwise, the most significant bit is kept high. So in other words, we clear the most significant bit to 0, and then we set the next significant bit 1 and all the other bits 0. Next, 0, 1, 0, 0 is converted again into analog form to obtain a new value VB. And if VB is still greater than VA, the output of the comparator is 0. And that makes the control logic to clear the second most significant bit to obtain 0, 0, sets the next most significant bit 1, and then the least significant bit to 0 to obtain a code 0, 0, 1, 0. And this continues until when VB is equals to or less than VA. This procedure continues until the control logic is able to obtain an approximation of the analog input voltage VA as a digital code stored in the register. And after all the bits have been tried, the register holds the digital equivalent of the analog input voltage VA. And that is why this converter is called a successive approximation converter, because it keeps approximating a digital code that is equivalent to the analog input voltage VA to be converted into digital form. And that is the operation of the successive approximation converter. The third type of the ADC is what we call the dual slope integration converter. Let me share the dual slope integration converter. Okay, this is the dual slope integration converter. It operates on the principle of charging and discharging of the capacitor, and hence the name dual slope integration converter. Charging and discharging of the capacitor. We have a set of two switches, T1 and T2, where T1 is connected to the analog voltage V in, which is to be converted into digital form. We have the integrator using the operational amplifier, a resistor in the forward path, and a capacitor in the feedback path. The output of the integrator goes into the comparator, the negative input terminal of the comparator. And as you can see, the positive input terminal of the comparator is connected to a ground, or is grounded. Then we have a control logic. The output of the comparator goes into a control logic circuit. And a clock signal is also an input to the control logic circuitry. Then a signal moves from the control logic circuit to a counter. And from the counter, we have the output of the counter giving us a digital output, which will be equivalent to the analog input signal to be converted into digital form. The conversion begins with the electronic switch in T1 position. So we start the operation of this counter with the switch at T1 position. So when it is at T1 position, you notice the capacitor at that point will start charging and is going to acquire a charge that is dependent upon the analog input voltage V in. So the capacitor is charging when we have the switch at T1 position. After T1 seconds have elapsed, then the control logic shifts the switch T1 to T2, so that now the switch is shifted to T2 position, this position. You notice that the voltage that is connected now to the resistor is a negative voltage, and therefore the capacitor will start discharging, since the potential difference here is a negative potential difference, and the capacitor starts discharging. The higher the input voltage V in, the greater the charge stored in the capacitor. So we said the output V out is going to depend on the analog input V in. And because the reference voltage is the opposite polarity to the analog input, then the capacitor is discharging. So because now the reference voltage is negative in potential, the capacitor starts discharging. At the same time, the control logic starts the counter. So at the same time, the control logic is going to start the counter, sends a signal to the counter to start a count. When the capacitor has fully discharged, the comparator output level goes to 0 when our V out is 0 and the potential difference across the positive input terminal is 0, the output of the comparator will go low. And that is going to hold the counter through the control logic signal. And at that point, the value that will have been stored in the counter is the digital equivalent of the analog input voltage V in. And through the charging and discharging of the capacitor, we are able to obtain a digital code which is equivalent to the analog input voltage V in. And that is the construction and operation of the dual slope integration converter in its conversion from analog to digital signals. The last ADC is what we call the flash ADC. Again, allow me to share the screen for the flash ADC. This is the flash ADC. And this is a typical flash ADC, which is made up of comparator networks as well as a priority encoder. So we have a priority encoder and some comparator, some sets of comparator networks. The input of the analog input signal is connected to the negative terminal of our comparators, as you can see. So this is our analog input voltage, which is fed into the negative input terminals of our comparators. Then we have resistor network to obtain a set of voltages by voltage divider theorem. So the potential difference at this point is 10 volts. So at this point we have 10 volts. And through the voltage divider network, we'll obtain different voltage levels. So at this point, you notice that these resistors, the total value of the resistors is 1, 2, 3, 4, 5, 6, 7 plus 3, which is 10. That means the potential difference at this point is going to be 7 volts. This is going to be 6 volts, 5 volts, 4 volts, 3 volts, 2 volts, and 1 volt. And this is what is compared with the analog input V in. If the analog input V in is greater than our voltage, then you notice that our output of the comparator is going to be high. But if V in is less than the voltage you're comparing with, then the output of the comparator is going to be low. Then the outputs of the comparators become input to the priority encoder, and we can have a tabulation of the inputs of the encoder as follows. You can have C1, this is C1, C2 all the way to C7, C3, C4, C5, C6, and C7 as the inputs to the priority encoder. And the output of the priority encoder is CBA, with C being the most significant bit and A the least significant bit. And we look at the operation of our comparator as follows. If our analog input voltage is less than 1 volt, if V in is less than 1 volt, you notice that our V in here is less than 1 volt and therefore C1 is going to be high. Since we'll be comparing 1 with a voltage less than 1, the output is high. Similarly, we are comparing this 1 with 2, and C2 will be high. And for all the input signals, C1 to C7, they will be high. And at that point, the output of the priority encoder will be 0, 0, 0. Then next, if V in is a voltage between 1 and 2, such that it is less than 2 volts, but our V in is greater than or equal to 1 volt. So if our V in is greater than or equal to 1 volt, but it is less than 2 volts, you notice at this point we will be comparing a voltage greater than 1 with 1, and at that point then C1 will be 0. In this point we'll have a 0. For all the other voltages, we are comparing with a voltage less than 2, and since at this point we have 2 volts, then C2 all the way to C7 will be high. And at this point, then C2 all the way to C7 will be high. And our output code at that point will be 0, 0, 1. Similarly, when we have a voltage between 2 and 3, so if V in is less than or equal to 2, but it is less than 3 volts, we notice that our C1 will be 0 because we are comparing a voltage which is greater than 2 with 1, so this will be 0. Here we are comparing a voltage again which is greater than 2 with 2, the output will be 0. But since that voltage is less than 3, then C3 will be 1 all the way to C7, and this will be 1, 1, 1, 1, 1. And at that point, the output code will be 0, 1, 0. This will continue until at last or finally, when our voltage is greater than or equal to 7 volts. When the voltage is greater than or equal to 7 volts, you notice we are comparing a voltage, let's say 7, with 1, and the output will be a 0. For all these other inputs, C1 all the way to C7, the outputs will be 0. And at that point, our digital output will be 1, 1, 1. With all the other voltages in between 3 and 7, giving us the digital equivalent between 0, 1, 0 and 1, 1, 1. And through that, we are able to obtain the digital equivalent of the analog input voltage using the flash ADC. And that is the operation of the flash ADC in its conversion of analog signals into digital codes. And there, it is the end of my presentation of the analog to digital converters. We've looked at 4 types of converters: the digital ramp converter, the successive approximation converter, the dual slope integration converter, and the flash ADCs. Otherwise, thank you for watching my video.